Welcome to our next lesson on machine learning. In today's lesson, we will be focusing on the fundamentals of classification and techniques for evaluating machine learning models. Without further ado, let's dive into the material, starting with the content on the following slide. At its core, classification is all about assigning instance or data points to predefined categories based on their features. This could be anything from determining whether an email is spam or not, to identifying the species of a plant based on its characteristics. Under the hood, classification models typically employ two key approaches: function estimation and probability prediction. Function estimation involves learning a mathematical function that maps input features to output categories, while probability prediction focuses on estimating the likelihood of an instance belonging to each possible category. Once we have our trained model, the next step is to predict the category for new, unseen instances. This is where the rubber meets the road, and we see how well our model generalizes to real-world data. But how do we know if our model is performing well? That's where model evaluation comes in. A crucial tool in our evaluation toolkit is the confusion matrix, which gives us a tabular summary of our model's performance, showing the counts of true positives, true negatives, false positives, and false negatives. From the confusion matrix, we can derive various evaluation metrics such as accuracy, precision, recall, and F1 score. These metrics provide different perspectives on our model's performance, allowing us to assess its strengths and weaknesses. Another powerful evaluation technique is the receiver operating characteristic curve, or ROC curve for short. The ROC curve plots the true positive rate against the false positive rate at different classification thresholds, giving us a visual representation of our model's performance. The area under the ROC curve, known as AUC, is a single scalar value that encapsulates the model's overall discriminatory power. By leveraging these evaluation techniques, we can gain deep insights into our classification models, identify areas for improvement, and make informed decisions about which models to deploy in production. So, there you have it, a whirlwind tour of classification basics and model evaluation. As we continue on our machine learning journey, we'll build upon these foundational concepts and explore more advanced techniques. But for now, let's take a moment to digest what we've learned and get ready to apply these ideas to real-world problems. Thank you for your attention, and let's keep pushing the boundaries of what's possible with machine learning. At its heart, classification is a supervised learning approach that involves categorizing instances based on their attribute characteristics. The key here is that the learning process is guided by a pre-labeled data set, known as the training set. This labeled data serves as a teacher, allowing the algorithm to learn the underlying patterns and relationships between the attributes and their corresponding categories. It's worth noting that the majority of classification problems and algorithms are tailored specifically for binary or binomial classification. In other words, they excel at distinguishing between two distinct categories. Think of scenarios like spam email detection, where an email is classified as either spam or not spam, or medical diagnosis, where a patient's test results indicate the presence or absence of a particular condition. However, what happens when we're faced with a multi-category classification problem? Fear not, because we have a clever strategy up our sleeves. The solution lies in leveraging multiple binary classifiers. By breaking down the multi-category problem into a series of binary classification tasks, we can effectively tackle more complex scenarios. For instance, let's say we're building a model to classify images of animals into three categories: cats, dogs, and birds. Instead of attempting to directly classify an image into one of the three categories, we can create three separate binary classifiers. One classifier would be trained to distinguish between cats and non-cats, another between dogs and non-dogs, and the third between birds and non-birds. By combining the prediction of these individual classifiers, we can accurately determine the category of a given animal image. This approach of decomposing multi-category problems into multiple binary classification tasks not only simplifies the learning process, but also allows us to leverage the strengths of specialized binary classification algorithms. As we progress through our journey into classification, we'll explore various algorithms, evaluation metrics, and techniques that empower us to build robust and accurate classifiers. By mastering these fundamentals, we'll be well equipped to tackle a wide range of real-world problems and drive meaningful insights from our data. So, let's embrace the power of classification and unlock the potential of supervised learning. With a solid understanding of these core concepts, there's no limit to the challenges we can conquer in the realm of data science and machine learning. At the core of any classifier lies the learning process, where the algorithm aims to discover a target function, commonly denoted as f. This function serves as a mapping mechanism, taking an attribute set X as input and assigning it to one of the predefined class labels, represented by Y. In essence, the target function f embodies the decision-making process of the classifier. In the realm of machine learning, we often refer to this target function as the classification model. It encapsulates the learned patterns and relationships between the input attributes and their corresponding class labels. The model acts as a blueprint, enabling the classifier to make predictions on new, unseen instances. Now, let's take a closer look at the input data that fuels the classification task. The data is typically organized as a collection of records, where each record is represented by a tuple, x, y. Here, x represents the attribute set, a collection of features or characteristics that describe the instance. These attributes can be numerical, categorical, or even textual in nature. On the other hand, I represents the class label associated with that particular record, indicating the category to which it belongs. The attribute set X serves as the foundation for the classifier's decision-making process. By analyzing the patterns and relationships within the attribute set, the classifier learns to discriminate between different classes. It identifies the distinguishing features that set each class apart from the others, allowing it to make accurate predictions on new instances. The class label Y, on the other hand, provides the ground truth or the actual category of each record in the training data. It acts as a supervisor, guiding the learning process and enabling the classifier to measure its performance and adjust its internal parameters accordingly. By working with this structured input data, consisting of attribute sets and their corresponding class labels, the classifier can learn the underlying patterns and build a robust classification model. The model, once trained, can then be applied to new, unseen instances to predict their class labels based on their attribute sets. As we delve deeper into the world of classification, we'll explore various algorithms and techniques that leverage this fundamental structure of input data and target functions. From decision trees and support vector machines to neural networks and ensemble methods, each approach brings its own unique perspective to solving classification problems. So, let's harness the power of classification and unlock the insights hidden within our data. By mastering these foundational concepts, we'll be well equipped to tackle complex real-world problems and drive meaningful outcomes in the ever-evolving landscape of data science and machine learning. At the heart of every classification task lies a classification algorithm, a systematic approach or logical framework that takes an input dataset, often referred to as the training set, and crafts a classifier tailored to the problem at hand. These algorithms come in various flavors, each bringing its own unique perspective and strengths to the table. Let's take a moment to highlight some of the most widely used classification techniques in the industry. One classic example is logistic regression, a statistical method that models the probability of an instance belonging to a particular class based on its input features. Decision trees, on the other hand, offer a hierarchical approach, recursively splitting the data based on the most informative attributes until a clear classification decision can be made. Neural networks, inspired by the structure and function of the human brain, have taken the world of machine learning by storm. These powerful models consist of interconnected nodes that learn intricate patterns and relationships within the data, enabling them to tackle complex classification tasks with remarkable accuracy. Support vector machines, or SVAD-BMs, take a geometric approach to classification. By finding the optimal hyperplane that separates different classes in a high-dimensional feature space, SVMs can effectively handle both linear and nonlinear classification problems. Naive Bayes, a probabilistic classifier based on Bayes' theorem, assumes that the input features are conditionally independent given the class label. Despite its simplicity, naive Bayes has proven to be surprisingly effective in various domains, especially when dealing with high-dimensional data. These are just a few examples of the diverse range of classification algorithms at our disposal. Each technique brings its own unique strengths, assumptions, and trade-offs, making it crucial to select the appropriate algorithm based on the specific characteristics of the problem at hand. Once a classification model has been learned from the training data, it becomes a powerful tool in our data science arsenal. We can leverage the model for two primary purposes: prediction and inference. In the realm of prediction, the trained model can be applied to new, unseen instances to assign them to one of the predefined classes. By feeding the model with the relevant input features, it can make informed decisions and provide accurate predictions, enabling us to make data-driven decisions and automate classification tasks. Beyond prediction, classification models also serve as valuable tools for inference and advice. By analyzing the learned patterns and relationships within the model, we can gain deep insights into the underlying factors that influence the classification outcomes. This knowledge can be harnessed to provide meaningful recommendations, guide decision-making processes, and uncover hidden trends within the data. As we continue our journey through the world of classification algorithms, we'll dive deeper into the intricacies of each technique, explore their strengths and limitations, and learn how to select the most appropriate algorithm for a given problem. By mastering these powerful tools, we'll be well equipped to tackle real-world classification challenges and drive impactful outcomes in the field of data science and machine learning. So, let's embrace the power of classification algorithms and unlock the full potential of our data. With a solid understanding of these techniques, there's no limit to the insights we can uncover and the solution we can develop. A classification model serves as a decision-making tool that takes in input data and outputs the corresponding target class label. It's like a highly trained expert that can look at a set of features and determine which category the instance belongs to. To build a robust classification model, we rely on a carefully curated dataset known as the training set. This dataset acts as the model's teacher, providing it with a diverse range of examples along with their correct class labels. By studying these examples, the model learns to recognize patterns, relationships, and discriminating factors that distinguish one class from another. Once the model has been trained on that training set, it's time to put it to the test. This is where the test set comes into play. The test set is a separate portion of the data that the model has never seen before. It serves as an unbiased evaluator, allowing us to assess how well the model generalizes to new, unseen instances. By comparing the model's predictions on the test set with the actual class labels, we can measure its performance and gauge its effectiveness. Now, it's important to note that there's no one-size-fits-all approach to building classification models. Just as there are various training algorithms available, each with its own strengths and weaknesses, there are also different ways to measure, the performance of the learned model. Some common evaluation metrics for classification models include accuracy, precision, recall, and F1 score. Accuracy measures the overall correctness of the model's predictions, while precision focuses on the proportion of true positive predictions among all positive predictions. Recall, on the other hand, quantifies the model's ability to identify all positive instances correctly. The F1 score provides a balanced measure that combines precision and recall into a single value. However, it's crucial to choose the appropriate evaluation metric based on the specific requirements of the problem at hand. In some cases, minimizing false positives may be more critical than maximizing overall accuracy. In others, identifying all positive instances, high recall, may be more important than precision. Understanding the trade-offs and aligning the evaluation metric with the business objectives is key to assessing the true performance of a classification model. As we dive deeper into the world of classification models, we'll explore various techniques for model selection, hyperparameter tuning, and performance optimization. We'll also delve into advanced topics such as ensemble methods, cross-validation, and handling imbalanced datasets. By mastering the art of building and evaluating classification models, we'll be well equipped to tackle real-world problems and drive data-driven decision-making. Whether it's detecting fraudulent transactions, predicting customer churn, or diagnosing medical conditions, classification models hold the key to unlocking valuable insights and making accurate predictions. So, let's embrace the power of classification models and harness their potential to transform raw data into actionable intelligence. With a solid understanding of these fundamental concepts and a keen eye for model evaluation, we'll be ready to take on the challenges of the ever-evolving landscape of data science and machine learning. When it comes to the outputs of a classification model, there are two primary forms: continuous output and discrete category prediction. While discrete category prediction is the most common and widely used, understanding the role of continuous output is crucial for gaining deeper insights into the model's decision-making process. Let's start with discrete category prediction. In this case, the classifier assigns each instance to one of the predefined categories or classes. It makes a definitive decision, labeling the instance as belonging to a specific class. For example, in a binary classification problem, the output would be either class A or class B. This type of output is straightforward and easy to interpret, making it the go-to choice for many classification tasks. However, there's more to the story than just the final class label. Many classifiers also produce continuous output, often in the form of probabilities. These probabilities provide a measure of confidence for each predicted class. For instance, a classifier might assign a probability of 0.51 to class A and 0.49 to class B. This indicates that while the model predicts class A, it's not entirely certain, and there's a close call between the two classes. On the other hand, if the classifier assigns a probability of 0.95 to class A and 0.05 to class B, it suggests a much higher level of confidence in the prediction. The probability values offer valuable insights into the model's decision-making process and can be particularly useful in scenarios where the cost of misclassification varies across different classes. It's important to note that not all classification algorithms produce probabilities as their continuous output. Some algorithms, such as neural networks, generate continuous outputs that require further interpretation. In these cases, a transformation step is necessary to convert the raw outputs into meaningful probabilities. One common transformation technique is the softmax function. It takes the raw output of a neural network and squashes them into a range between 0 and 1, ensuring that they sum up to 1. This normalization process allows us to interpret the outputs as probabilities, providing a more intuitive understanding of the model's predictions. The choice between using discrete category predictions or continuous outputs depends on the specific requirements of the problem at hand. In some cases, the final class label is all that matters, and the discrete output suffices. However, in situations where the confidence of predictions is crucial, such as in medical diagnosis or fraud detection, the continuous output provides valuable additional information. As we continue our exploration of classification models, we'll delve into various techniques for handling and interpreting classifier outputs. We'll discuss strategies for setting appropriate classification thresholds, dealing with imbalanced datasets, and leveraging the continuous outputs for advanced analysis and decision making. By understanding the nuances of classifier outputs and harnessing the power of both discrete and continuous predictions, we can build more robust and informative classification models. Whether we're aiming for crisp class labels or seeking deeper insights into the model's confidence, the choice of output format plays a crucial role in shaping the effectiveness of our classification solutions. So, let's embrace the diversity of classifier outputs and leverage them to drive meaningful insights and informed decision-making. With a solid grasp of these concepts, we'll be well equipped to tackle the complex challenge that lie ahead in the realm of data science and machine learning. First and foremost, it's absolutely critical to evaluate your model using appropriate metrics. Choosing the right evaluation metric is essential to understanding how well your model performs and whether it meets the specific requirements of your problem. Whether you're using accuracy, precision, recall, F1 score, or any other metric, it's crucial to align the evaluation criteria with your business objectives and the nature of your data. One of the biggest pitfalls in model evaluation is overfitting. An overfit model is one that performs exceptionally well on the training data, but fails to generalize to new, unseen instances. It's like a student who memorizes the answers to a specific set of questions, but struggles when faced with new problems. Overfitting occurs when a model learns the noise and idiosyncrasies of the training data, rather than capturing the underlying patterns and relationships. To safeguard against overfitting, it's essential to use techniques that assess the model's performance on independent data. One common approach is to split your data into separate training and testing sets. The training set is used to build and fine-tune the model, while the testing set serves as an unbiased evaluator, providing a realistic assessment of the model's performance on unseen data. However, relying on a single train-test split can be problematic, as the evaluation results may vary depending on how the data is divided. To mitigate this issue, it's recommended to use multiple random splits, each with a different random seed. By evaluating the model across multiple splits, you can obtain a more robust and reliable estimate of its performance. Another powerful technique for model evaluation is cross-validation. In cross-validation, the data is partitioned into multiple subsets, or folds. The model is trained and evaluated iteratively, using different combinations of folds for training and testing. Common variants include k-fold, cross-validation, and stratified k-fold cross-validation, which ensure that each fold maintains a representative distribution of the target classes. Cross-validation provides a more comprehensive assessment of the model's performance, as it evaluates the model under different data configurations. By averaging the evaluation metrics across the folds, you can obtain a more stable and reliable estimate of the model's generalization ability. It's important to note that the evaluation process should be carried out using independent samples that were not used during the model training phase. Using the same data for both training and evaluation can lead to overly optimistic and misleading results. By strictly separating the training and evaluation data, you can ensure an unbiased assessment of the model's true performance. As we delve deeper into model evaluation, we'll explore advanced techniques such as nested cross-validation, learning curves, and model selection strategies. These techniques allow us to fine-tune our models, identify potential issues, and select the best performing model for deployment. By embracing rigorous model evaluation practices, we can build classification models that are not only accurate, but also reliable and trustworthy. We can make informed decisions, assess the model's limitations, and communicate its performance to stakeholders with confidence. So, let's make model evaluation a top priority in our data science workflow. By using appropriate metrics, safeguarding against overfitting, and leveraging techniques like cross-validation, we can unlock the true potential of our classification models and drive impactful results in the real world. Overfitting occurs when a model becomes too complex and starts to memorize the noise and idiosyncrasies of the training data rather than learning the underlying patterns and relationships. It's like a tailor who creates a suit that fits the mannequin perfectly, but fails to accommodate the variation in real human bodies. An overfit model may exhibit excellent performance on the training data, but struggle to generalize to new, unseen instances. The consequences of overfitting can be severe. An overfit model may make predictions that are overly confident but incorrect, leading to poor performance in real-world scenarios. It may also fail to capture the true underlying patterns in the data, limiting its ability to provide meaningful insights and make accurate predictions. So, how can we detect and mitigate overfitting? One key indicator is a significant discrepancy between the model's performance on the training data and its performance on independent test data. If the model achieves near perfect accuracy on the training set, but performs poorly on the test set, it's a clear sign of overfitting. To combat overfitting, we have several strategies at our disposal. One fundamental approach is to use regularization techniques. Regularization adds a penalty term to the model's objective function, discouraging it from becoming too complex. Common regularization methods include L1 regularization, lasso, which encourages sparse feature selection, and L2 regularization, ridge, which promotes smaller weights across all features. By controlling the complexity of the model, regularization helps prevent overfitting and improves generalization. Another effective strategy is to employ cross-validation, as we discussed in our previous presentation. By evaluating the model's performance across multiple folds of the data, cross-validation provides a more robust assessment of its generalization ability. It helps identify whether the model is consistently performing well or if it's overfitting to specific subsets of the data. In addition to regularization and cross-validation, there are other techniques to mitigate overfitting. One approach is to simplify the model architecture by reducing the number of features or the depth of the model. By focusing on the most informative features and avoiding unnecessary complexity, we can improve the model's ability to generalize. Data augmentation is another powerful technique, particularly in domains like computer vision and natural language processing. By applying controlled transformation to the training data, such as rotations, translations, or synonym replacements, we can artificially increase the diversity of the training set. This helps the model learn more robust and generalizable patterns, reducing the risk of overfitting. It's important to note that the battle against overfitting is an ongoing process. As we iterate on our models and incorporate new data, we must continuously monitor their performance and be vigilant for signs of overfitting. By employing a combination of regularization, cross-validation, model simplification, and data augmentation techniques, we can build models that are not only accurate, but also reliable and generalizable. So, let's make overfitting a top priority in our model evaluation workflow. By understanding its implications, detecting its presence, and employing effective mitigation strategies, we can develop classification models that are robust, trustworthy, and capable of delivering valuable insights in real-world scenarios. Remember, the goal is not just to create models that excel on the training data, but to build models that can generalize and make accurate prediction on unseen data. By keeping overfitting in check, we can unlock the true potential of our machine learning models and drive meaningful impact in the field of data science. At its core, A confusion matrix is a tabular summary of a classification model's predictions compared to the actual ground truth labels. It provides a clear and concise way to visualize the model's performance across different classes, highlighting the instance where the model made correct predictions and where it encountered confusion or misclassification. To understand the structure of a confusion matrix, let's consider a binary classification problem with two classes, positive and negative. The confusion matrix for this scenario would be a 2x2 table, where the rows represent the actual classes and the columns represent the predicted classes. The four cells of the confusion matrix hold valuable information. The top left cell, known as the true positive, TP, represents the instances that were correctly predicted as positive. The bottom right cell, called the true negative, TN, represents the instances that were correctly predicted as negative. On the other hand, the top right cell, referred to as the false positive, FP, represents the instances that were incorrectly predicted as positive when they were actually negative. Similarly, the bottom left cell, known as the false negative, FN, represents the instances that were incorrectly predicted as negative when they were actually positive. The confusion matrix provides a wealth of information for evaluating the model's performance. From the matrix, we can derive several key metrics. Accuracy, which measures the overall correctness of the model's predictions, can be calculated by summing the true positives and true negatives and dividing by the total number of instances. Precision, which focuses on the model's ability to correctly identify positive instances, is calculated as the ratio of true positives to the sum of true positives and false positives. Recall, also known as sensitivity, measures the model's ability to capture all the positive instances and is calculated as the ratio of true positives to the sum of true positives and false negatives. The F1 score is another commonly used metric that provides a harmonic mean of precision and recall, balancing both aspects of the model's performance. By analyzing the confusion matrix, we can gain insights into the model's strengths and weaknesses. For example, a high number of false positives may indicate that the model is overly sensitive and needs adjustments to reduce false alarms. On the other hand, a high number of false negatives suggests that the model is failing to capture important positive instances and may require further refinement. It's important to note that the confusion matrix can be extended to multi-class classification problems as well. In these cases, the matrix becomes an NXN table, where n represents the number of classes. The diagonal elements of the matrix represent the correctly classified instance for each class, while the off-diagonal elements indicate the misclassification between different classes. By leveraging the confusion matrix, we can gain a comprehensive understanding of our model's performance, identify areas for improvement, and make informed decisions about model selection and optimization. As we continue our journey in model evaluation, we'll delve into advanced techniques such as precision recall curves, ROC curves, and multi-class evaluation metrics. These tools will further enhance our ability to assess and fine-tune our classification models. So, let's embrace the power of the confusion matrix and use it as a guiding light in our quest for building accurate, reliable, and insightful classification models. By understanding the intricacies of the confusion matrix and leveraging its insights, we can make data-driven decisions and drive meaningful impact in the field of machine learning and data science. At first glance, accuracy seems like a straightforward and intuitive measure of a classifier's performance. It quantifies the proportion of instances that are correctly classified by the model. Mathematically, accuracy is defined as the number of correctly categorized items divided by the total number of items. Accuracy provides a quick and easy to understand summary of the model's overall correctness. A higher accuracy value indicates that the classifier is making more correct predictions across all classes. However, It's important to recognize that accuracy has its limitation and can be misleading in certain scenarios. One notable case is when dealing with unbalanced classes, where the distribution of instance across different classes is highly skewed. Consider a binary classification problem, where the positive class is extremely rare, such as detecting fraudulent transactions in a financial dataset. If the dataset contains 99% legitimate transactions and only 1% fraudulent ones, a naive classifier that always predicts legitimate would achieve an accuracy of 99%. However, this high accuracy is misleading because the classifier completely fails to identify any fraudulent transactions, which are the critical instances of interest. In such cases, accuracy alone does not provide a comprehensive picture of the model's performance. It fails to capture the nuances and trade-offs between different types of errors, such as false positives and false negatives. Moreover, accuracy treats all types of errors equally, without considering the varying costs or consequences associated with different misclassifications. In some domains, such as medical diagnosis or fraud detection, the cost of a false negative, missing a positive instance, may be much higher than the cost of a false positive, incorrectly flagging a negative instance. To address these limitations, it's essential to consider additional evaluation metrics that provide a more nuanced view of the classifier's performance. Precision, recall, and F1 score are commonly used metrics that focus on the model's ability to correctly identify positive instances while accounting for the balance between false positives and false negatives. Precision measures the proportion of true positive predictions among all positive predictions, while recall quantifies the model's ability to capture all positive instances. The F1 score combines precision and recall into a single metric, providing a balanced measure of the model's performance. In addition to these metrics, it's crucial to consider domain-specific evaluation criteria and align the evaluation process with the specific goals and requirements of the problem at hand. By carefully selecting and interpreting evaluation metrics, we can gain a more comprehensive understanding of our classifier's strengths and weaknesses. As we continue our journey in model evaluation, we'll explore advanced techniques such as cost-sensitive evaluation, multi-class metrics, and model comparison strategies. These approaches will further enhance our ability to assess and optimize our classification models. So, let's embrace the power of accuracy while recognizing its limitations. By complementing accuracy with additional evaluation metrics and considering the specific characteristics of our problem domain, we can make well-informed decisions and build classifiers that deliver meaningful and reliable results. Remember, the goal is not just to achieve high accuracy, but to develop models that align with our business objectives, capture the nuances of the data, and drive impactful outcomes in real-world scenarios. By taking a comprehensive and thoughtful approach to model evaluation, we can unlock the true potential of our classification models and make significant contribution in the field of data science. Precision and recall are complementary metrics that provide a more granular view of a classifier's ability to correctly identify instances of a particular class. Let's explore each of these metrics in detail. Precision focuses on the accuracy of the classifier's positive predictions. It measures the fraction of instances that the classifier flags as belonging to a specific class that actually belong to that class. In other words, precision quantifies how precise or exact the classifier is when making positive predictions. A high precision indicates that when the classifier predicts an instance as positive, it is highly likely to be correct. This is particularly important in scenarios where false positives have significant consequences, such as in spam email detection or medical diagnosis. On the other hand, recall focuses on the classifier's ability to identify all instances of a particular class. It measures the fraction of instances in a class that are successfully detected by the classifier. Recall quantifies how well the classifier captures the positive instances, ensuring that no relevant instances are missed. A high recall indicates that the classifier is able to identify a large proportion of the positive instances, minimizing the number of false negatives. This is crucial in scenarios where missing positive instances can have severe consequences, such as in fraud detection or disease diagnosis. It's important to note that precision and recall are often in tension with each other. Improving precision often comes at the cost of lower recall and vice versa. The choice between optimizing for precision or recall depends on the specific requirements and priorities of the problem at hand. To balance the trade-off between precision and recall, the F1 score is commonly used. The F1 score is the harmonic mean of precision and recall, providing a single metric that captures both aspects of the classifier's performance. As we continue our journey in model evaluation, we'll explore advanced techniques such as precision recall curves, which allow us to visualize the trade-off between precision and recall at different classification thresholds. We'll also delve into multi-class evaluation metrics and strategies for optimizing classifiers based on specific business objectives. By leveraging precision and recall, along with other evaluation metrics, we can gain a comprehensive understanding of our classifier's strengths and weaknesses. We can make informed decisions about model selection, threshold optimization, and fine-tuning to align with the specific requirements of our problem domain. So, let's embrace the power of precision and recall in our model evaluation toolkit. By carefully analyzing these metrics and considering the specific characteristic of our data and business goals, we can build classifiers that deliver accurate, reliable, and actionable insights. Remember, the ultimate goal is to develop models that not only achieve high-performance metrics, but also drive meaningful impact in real-world scenarios. By taking a holistic approach to model evaluation, considering precision, recall, and other relevant metrics, we can unlock the true potential of our classification models and make significant contribution in the field of data science. The F1 score is a powerful metric that combines precision and recall into a single value, providing a balanced measure of a classifier's performance. It is especially useful when we need to find an optimal balance between precision and recall, ensuring that our model achieves high accuracy while minimizing both false positives and false negatives. Let's break this down. Precision, as we discussed earlier, measures the proportion of true positive predictions among all positive predictions. It focuses on the accuracy of the classifier's positive predictions. On the other hand, recall quantifies the classifier's ability to identify all positive instances, ensuring that no relevant instances are missed. The F1 score takes the harmonic mean of precision and recall, giving equal weight to both metrics. By using the harmonic mean instead of the arithmetic mean, the F1 score penalizes extreme values and favors a balance between precision and recall. The F1 score ranges from 0 to 1, with 1 being the best possible score and 0 being the worst. A high F1 score indicates that the classifier has achieved a good balance between precision and recall, effectively identifying positive instances while minimizing false positives and false negatives. It's important to note that the F1 score is sensitive to changes in either precision or recall. If a classifier improves precision at the expense of recall or vice versa, the F1 score will decrease. This property makes the F1 score a valuable tool for evaluating classifiers in scenarios where both precision and recall are equally important. For example, consider a medical diagnosis task where we want to identify patients with a specific condition. In this case, both precision and recall are crucial. We want to minimize false positives to avoid unnecessary treatments or procedures. but we also want to minimize false negatives to ensure that no patients with the condition are missed. The F1 score provides a comprehensive measure of the classifier's performance in such scenarios. As we continue our journey in model evaluation, we'll explore techniques for optimizing classifiers based on the F1 score. We'll discuss strategies for finding the optimal classification threshold that maximizes the F1 score, as well as methods for handling class imbalance and improving the overall performance of our models. By leveraging the F1 score, along with other evaluation metrics, we can gain a deeper understanding of our classifier's strengths and weaknesses. We can make informed decisions about model selection, parameter tuning, and feature engineering to develop classifiers that deliver accurate and reliable results. So, let's embrace the power of the F1 score in our model evaluation toolbox. By carefully analyzing this metric and considering the specific requirements of our problem domain, we can build classifiers that strike the right balance between precision and recall, ultimately driving meaningful impact in real-world applications. Remember, the goal is not just to achieve high F1 scores, but to develop models that align with our business objectives and deliver actionable insights. By taking a comprehensive approach to model evaluation, considering the F1 score alongside other relevant metrics and domain knowledge, we can unlock the true potential of our classification models and make significant contribution in the field of data science. Sensitivity and specificity provide a more nuanced view of a classifier's ability to correctly identify positive and negative instances, respectively. Let's dive into each of these measures in more detail. Sensitivity, also known as the true positive rate or recall, focuses on the classifier's ability to correctly identify positive instances. It measures the proportion of actual positive instances that are correctly predicted as positive by the classifier. A high sensitivity indicates that the classifier is able to capture a large proportion of the positive instances, minimizing the number of false negatives. This is particularly important in scenarios where missing positive instances can have severe consequences, such as in medical diagnosis or fraud detection. On the other hand, specificity, also known as the true negative rate, focuses on the classifier's ability to correctly identify negative instances. It measures the proportion of actual negative instances that are correctly predicted as negative by the classifier. A high specificity indicates that the classifier is able to accurately identify a large proportion of the negative instances, minimizing the number of false positives. This is crucial in scenarios where false positives can lead to unnecessary actions or costs, such as in spam email detection or medical screening. It's important to note that sensitivity and specificity are often in tension with each other. Improving sensitivity may come at the cost of lower specificity, and vice versa. The choice between optimizing for sensitivity or specificity depends on the specific requirements and priorities of the problem at hand. Poor classifiers tend to perform worse on at least one of these two measures. A classifier with low sensitivity may miss a significant number of positive instances, while a classifier with low specificity may incorrectly classify many negative instances as positive. As we continue our journey in model evaluation, we'll explore techniques for optimizing classifiers based on sensitivity and specificity. We'll discuss strategies for finding the optimal classification threshold that balances these measures, as well as methods for handling class imbalance and improving the overall performance of our models. By leveraging sensitivity and specificity, along with other evaluation metrics, we can gain a comprehensive understanding of our classifier's strengths and weaknesses. We can make informed decisions about model selection, parameter tuning, and feature engineering to develop classifiers that align with the specific requirements of our problem domain. So, let's embrace the power of sensitivity and specificity in our model evaluation toolkit. By carefully analyzing these measures and considering the specific characteristic of our data and business goals, we can build classifiers that deliver accurate and reliable results, ultimately driving meaningful impact in real-world applications. Remember, the ultimate goal is to develop models that not only achieve high-performance metrics, but also align with our business objectives and deliver actionable insights. By taking a holistic approach to model evaluation, considering sensitivity, specificity, and other relevant metrics, we can unlock the true potential of our classification models and make significant contributions in the field of data science. Performance charts provide visual representation of various evaluation metrics, allowing us to make informed decisions and optimize our models effectively. Let's dive into some of the most common performance charts used in the industry. First, we have the receiver operating characteristic, ROC curve. The ROC curve is a powerful tool that plots the true positive rate, sensitivity, against the false positive rate, specificity, at different classification thresholds. It provides a comprehensive view of the classifier's performance across the entire range of possible thresholds. The ROC curve allows us to assess the trade-off between sensitivity and specificity. A perfect classifier would have an ROC curve that hugs the top left corner, indicating high sensitivity and high specificity. The area under the ROC curve, AUC, is a scalar value that summarizes the overall performance of the classifier, with a higher AUC indicating better discriminatory power. Next, we have the sensitivity specificity chart. This chart plots the true positive rate, sensitivity, against the true negative rate, specificity, at different classification thresholds. It provides a direct comparison of the classifier's ability to correctly identify positive and negative instances. The sensitivity and specificity chart helps us understand how well the classifier balances the trade-off between capturing positive instances and avoiding false positives. It allows us to select an optimal threshold that aligns with our specific requirements, such as prioritizing high sensitivity or high specificity. Another valuable chart is the lift chart. The lift chart measures the relative increase in predictive performance compared to a random baseline. It plots the lift, which is the ratio of the classifier's predictive performance to the random baseline, against the rate of positive predictions. The lift chart helps us assess the effectiveness of our classifier in targeting the most likely positive instances. A higher lift indicates that the classifier is able to identify positive instances more efficiently than random selection. It is particularly useful in scenarios where resources are limited, and we need to prioritize the instances most likely to be positive. Lastly, we have the precision site recall chart. This chart plots the precision, which is the proportion of true positives among the predicted positives, against the recall, sensitivity, at different classification thresholds. It provides insights into the classifier's ability to balance precision and recall. The precision recall chart is especially relevant when dealing with imbalanced datasets or when the costs of false positives and false negatives differ. It allows us to select an optimal threshold that maximizes precision while maintaining an acceptable level of recall or vice versa, depending on our specific requirements. While each performance chart offers unique insights, the ROC curve is arguably the most popular and widely used. It provides a comprehensive assessment of the classifier's performance, allowing for easy comparison between different models and facilitating model selection based on the AUC metric. As we continue our journey in model evaluation, we'll explore techniques for interpreting and leveraging these performance charts. We'll discuss strategies for selecting optimal thresholds, comparing multiple models, and communicating the results effectively to stakeholders. By utilizing performance charts, along with other evaluation metrics and domain knowledge, we can gain a holistic understanding of our classifier's strengths and weaknesses. We can make data-driven decisions to optimize our models, align them with business objectives, and deliver impactful results in real-world applications. So, let's embrace the power of performance charts in our model evaluation toolkit. By carefully analyzing these visual representations and considering the specific requirements of our problem domain, we can build robust and reliable classification models that drive meaningful insights and decision-making. Remember, the ultimate goal is to develop models that not only achieve high performance metrics, but also align with our business objectives and deliver actionable insights. By taking a comprehensive approach to model evaluation, leveraging performance charts alongside other relevant metrics and domain expertise, we can unlock the true potential of our classification models and make significant contributions in the field of data science. Cross-validation, or CV for short, is a sophisticated approach that allows us to create multiple, independent training and testing samples, while still utilizing the entire dataset for both modeling and evaluation. It addresses the fundamental challenge of assessing a model's performance on unseen data and provides a more reliable estimate of its true predictive power. At its core, cross-validation involves partitioning the dataset into several subsets or folds, and iteratively using each fold as a testing set, while the remaining folds serve as the training set. This process is repeated multiple times, with each fold taking its turn as the testing set. By doing so, cross-validation ensures that every instance in the dataset has an opportunity to be part of both the training and testing process. One of the key advantages of cross-validation is its ability to mitigate overfitting, a common pitfall in machine learning where a model becomes too specialized to the training data and fails to generalize well to new unseen instances. By creating multiple independent training and testing samples, cross-validation reduces selection bias and helps assess the model's performance under different data configurations. Moreover, cross-validation plays a crucial role in reducing prediction variance. By averaging the performance metrics across multiple folds, cross-validation provides a more stable and reliable estimate of the model's true performance. This is particularly important when dealing with limited or noisy datasets, as it helps smooth out any anomalies or fluctuations that may arise from a single train-test split. When working with imbalanced datasets, where the distribution of classes is skewed, it's essential to stratify the folds during cross-validation. Stratification ensures that each fold maintains a representative distribution of the target classes, mirroring the overall class proportion in the dataset. This is crucial for obtaining accurate performance estimates and avoiding bias towards the majority class. There are several common cross-validation techniques, each with its own strengths and considerations. K-fold cross-validation is a popular choice, where the dataset is divided into k equally sized folds. The model is trained and evaluated k times, with each fold serving as the testing set once. Another variant is stratified k-fold cross-validation, which incorporates stratification to handle imbalanced datasets effectively. Leave one out cross-validation, LOOCV, is an extreme case of k-fold cross-validation, where k is equal to the number of instances in the dataset. In LOOCV, each instance takes its turn as the testing set, while the remaining instances form the training set. Although computationally intensive, LOOCV can be useful for small datasets or when a thorough evaluation is required. As we continue our journey in model evaluation, we'll explore best practices for implementing cross-validation and interpreting its results. We'll discuss strategies for selecting the appropriate cross-validation technique based on the characteristics of our dataset and the specific requirements of our problem domain. By leveraging cross-validation, along with other evaluation metrics and techniques, we can gain a comprehensive understanding of our model's performance and make informed decisions to optimize its generalization capabilities. So, let's embrace the power of cross-validation in our model evaluation toolkit. By carefully designing and executing cross-validation experiments, we can build models that are robust, reliable, and capable of delivering accurate predictions on unseen data. Remember, the ultimate goal is to develop models that not only achieve high-performance metrics, but also generalize well to real-world scenarios. By taking a rigorous approach to model evaluation, leveraging cross-validation alongside other relevant techniques and domain expertise, we can unlock the true potential of our machine learning models and make significant contributions in the field of data science. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.